12-2, day 1. We're still focused on regression and coming up with linear models, but this example here really gets to the point of section 2. Okay, it's about transforming data in order to use a linear model. Okay, we've got data for a scatter plot on this first slide. It's on the Atlantic rockfish, otherwise known as the striped bass. Big fish, I think it's commonly a sport fish, not so much for, I don't know, maybe people eat it. It's a common sport fish. It's big, heavy, probably hard to catch. If you look up pictures, they're those fish that are like the size of people practically when they catch them. That relates its length to its weight. And we head down here and look what we find. This compares x to y, and we see a model. Now, you might think, oh, it looks exponential, or it looks quadratic. You're kind of, I mean, if you're thinking that, you're on the right track. We shouldn't jump to what type it is, because that's kind of the point of this section, is to figure that out as best we can. When you look at that data for x and y, what I want you to think is clearly not linear. And that's all the farther you got to go. It's clearly not linear. Okay? Now, we'd like to come up with a model to make predictions about weight from length, but up until now, all we have is models for regression lines. Okay? Now, take a look at what happens here. This point is when the transformation has happened. We have transformed one of the variables, and you will see this scatter plot does not compare length to weight. It compares length cubed to weight. Length cubed to weight. That model, it looks pretty linear. Okay? Now, those points seem to form a line, and couldn't we, in theory, find a regression line that related those two variables? And we absolutely can, right? And as long as it meets all of our conditions and seems appropriate to use linear regression, that's what we would do, is let's look at the length cubed and the weight. It's not ideal, but remember back over here, if we want to use a line, which you'll see this whole section we do, that's the method, that's the means that we have to make predictions about an association of two numerical variables. That's what we have. We can't compare x directly to y because it's not linear. Okay, we see that from the scatter plot. How about another option? What could we do x and then compare that to the cube root of the weight? That's the transformation, and once again, that data looks pretty linear. That could be a model that we work with as well. Well, let's get some Minitab output and compare the two. And now what you have to watch out for here is, this is something that'll come up time and time again in section 2. When you're dealing with Minitab output and you've done a transformation, pay really close attention to what variables that you're dealing with. Okay, for this first one, this is comparing the length cubed of the fish to its weight. This one is comparing the length to the cube root of its weight. Okay? What you often find that people do is they just drift back into comparing x to y. And that's not what's happening here. Okay? This is Minitab output for a regression line. There's r squared, looks solid. Transformation 2 actually looks even a little bit better. But here, if I were to write the line for number 1, this one will give me the weight of the fish. Okay, the y-intercept for this line is 4.066. The slope is 0.0146774, and at that point it gets so tempting to just throw in an x and call it good, but if we do that, we're comparing x to y. And remember the variables that we have. This is transformed data. X has to be cubed. So the very first thing that we do if we plug in a length is we have to take that length and cube it before we multiply it by the slope or the y-intercept. Let's go down and look at transformation number 2. This one will make a prediction, but it will not directly give us the weight. It'll be the cube root. It's a number that's going to help us get the weight. It's just not the weight of the fish itself. There's my y-intercept. Here's my slope. And here it is just x, which leads me back over here. I don't think I actually finished writing x. This doesn't compare the number 1 to the cube root of y. It compares x. Maybe I was thinking that was an L. But I've done x and y the whole time. I should stick with that. So if you substitute a value for x and look at its length, okay, it will give us a y value here or an answer, but that number needs to be cubed to get back to the fish's weight. Okay? Keep very close track of what variables you have. Now, this is still on the data with the fish. Here was transformation 1, here was 2. We saw that r squared was really high. We had a really strong association. Now, we shouldn't jump to a situation where we're going to use those models to make predictions without looking at their residual plots. Here they are. As always with the residual plots, we're looking for patterns, and you know, I don't see any. So transformation 1 looks like a really good model to predict the weight of the fish, and you know, so does 2. 2 looks a little bit better because the r squared value was a little higher, but both would be very good. Another tool that we will use to do transformations are logarithms. They work very well and tends to be the more common route that we go. And that past one, we saw those 2 transformations. One we used, you know, cubing the x variable, and the other we used a cube root for y. But often we use logarithms. Here, somewhere it's got it. I'll take you through the steps here to do it, though. In fact, this leaves good room for like a side-by-side comparison. One of the slides already has this work for doing an exponential model. But what the heck, I lost track of where it was, so maybe it's still to come. We're saying that an exponential model is y equals ab to the x power. I don't think it has the derivation for a power, but let's say that's ax to the n. Okay? In the exponential model, a and b are constants. In the power, a and n. Right? X and y are the only variables. So here's how it works if we choose to use logarithms to do the transformation. Take the log of both sides. From an algebra perspective, that's a completely valid step to make. Log of y leaves us with absolutely nothing to simplify. Log of ab to the x power gives us plenty. We could take the terms a and b to the x power, and we could split them up. One final step of log of a plus x log b. Now, if you look real close, we have ourselves a line. Log of a, which is a constant, is like our y-intercept. Log of b, well, that is our slope. So here we go. If we think the model is exponential for our transformation, we would go ahead and compare x to the log of the y variable. Okay, pretty slick way to do it. Now, I'm running out of room here in terms of width. Let me see if I can scoot this over and find a little more. I think I'm good. The power model, let's do the exact same thing. I'll need to write smaller though. Log of y is log of ax to the n. It's the same three steps that I'm going to do. You're just going to see it's going to come out to a slightly different transformation. Log of a plus log of x to the n power. And finally, log of a plus x, excuse me, not x, n log x. Okay? Remember that x and y are the variables, so this again forms a line. Think of n as the slope, log of a as the y-intercept. This, however, compares the log of x to the log of y. So if I take the logarithm of both variables, that is kind of checking to see if the original data has a power model. Okay? But we'll work with those two a lot, and when you see in the notes referring to transforming with logarithms, this is what they're talking about. This is not an example I'm going to work through, but it's illustrating an example of data that follows exponential growth. Whoops, there it is. The derivation, I knew it was somewhere. It was just farther down in the notes. This doesn't have both, it just has the exponent. Hopefully you see that and it looks extremely familiar. 2 slides ago we just did that, but that's all it's saying. Alright, let's get some more exponential data. This looks at the number of transistors in computer chips and how that has changed over time. It's increased, and it's increased exponentially. In other words, computing power has gotten significantly better since 1970. Okay, that shouldn't surprise anybody. But there's the data we have, and just to stay focused on the variables, the number of years since 1970 is x, the number of transistors in the chips is y. Okay, it looks like the data is exponential, but let's investigate that with a transformation. Alright, take a look at what we have here. Nothing has been done with x. Right? Remember, we looked at that data and we were kind of thinking exponential. So we left x alone, but for all the data we had about transistors, we took the natural log. Okay, this scatter plot looks pretty linear, which would tell us perhaps an exponential model is the case between x and y. But as we work with this transformation, because the next step is to go get a regression line, okay, we are comparing x, just regular old x, to the natural log of y. Okay, this is a big thing to be able to do here. Okay, now one thing, I'm not going to use this to make a prediction, because you can see the residuals got all kinds of, lovely patterns going on. But this is, so that would concern me. If I'm thinking about my conditions, for the linear one, I should see a strong association, which I do. My residual plot shows a pattern. I don't like that, but okay, I'm just pointing out that that's there. Writing, this is a big thing for this section, writing the line from the Minitab output. The top number that I've circled there is the y-intercept, and the bottom number is the slope. Okay, so here it is. 0.647 plus 0.36583x. X is the number of years since 1970. I could go ahead and I could just plug that in. Over here, this part is huge. Okay, this is another part where everybody just tends to drift back and thinks, oh, we're comparing X and Y. Not the case. This will predict not the number of transistors, but the natural log of the number of transistors in the computer chip. A valuable number, no doubt about it. Okay, but it doesn't go directly to the number of transistors in the chip. Okay, just the natural log. All right, I want to make the next step and use the line to make a prediction, but I want to start with a relatively simple context. So when you hear of exponential models, I bet you a lot of you think of population growth, which so often follows exponential growth. So here I have some data from 1790 to 1880, right? The early years of America. Here we are. Again, keeping track of variables. There is the comparison of X to Y. What do you notice about that scatter plot? Very much not linear. Here is X to ln of Y. That does look linear. With our Minitab output, it is this one right here. That's the one we're going to work with. Okay? Now let's be pretty thorough here as we do this. The starting point before I use my line is I should define my variable. Variables, I should say. X is, I believe it said it was the number of years after 1700. Which would make Y the U.S. population. And it did specify that that was in millions of people. Here is my regression line. Those are the numbers I want. Two, 8, 7, 2, 8. I'm using this to make calculations, so I'm being picky and I want lots of decimals because, final answers I'm okay with rounding to either 2 or 3 decimal places, but if I'm going to use these to make calculations, I want more of them. And be careful about that part. Okay? Be careful right there. Okay, so that we did before on the transistor model with the computer chips. Okay, we did that. Now, here's the next step. Let's use this to make a prediction. Okay, let's use it to make a prediction. 1890 corresponds to 190 years after 1700. I need to plug in that value. Okay? Now once I do that, this right side, I just go ahead and simplify. And I would get 4.26521. Okay? Now, don't just stop there and say, there's our answer. That's in millions of people. Okay? If you go back to the original scatter plot, you'll see you have an answer that makes no sense. The population is going up. It's going up exponentially. And then, you know, barring some type of like zombie-like plague that would have hit the United States between 1880 and 1890, I don't think we lost 90% of the population in 10 years. Okay? The issue is, to take care of this, we need to take both sides of the equation and raise them as exponents to base e. That will take care of that natural log. We can't just have it disappear on its own, but we end up with this. Okay, I mean, again, this model doesn't predict the population, but it gives us a very relevant number. It's the natural log of the population. So if we take e to that power and just punch it into our calculator, we get an answer of 71.18 million people. Makes way more sense than 4.2. That's our prediction for the population in 1890. Okay? Don't forget this last step. It gets overlooked way more often than you would think. All right, here's another fun one out in astronomy. This is 2005 data. Remember, in 2006, Pluto lost its status as a planet. I know, sad. But it fits the measurements. It's orbiting the sun, so whether it's a planet or not, we'll take it. That's fine. X is the distance from the sun. Y is the amount of time it takes for that planetary body. Celestial body, I guess I should say. I shouldn't say planetary. You get the idea. Okay? We're talking about big things that orbit the sun. Most of them planets. X is measured in astronomical units. That's 1 Earth distance from the sun. Okay? So if you see Pluto, we'll give Pluto a shout out here because it's lost its status as a planet. It's almost 40 times farther away from the sun than the Earth. And a year on Pluto is like 248.5 Earth years. Okay? It takes a long time. There's X to Y. Not linear, right? That's all we're looking for. That's the whole point of all this. Not linear. Here we have 2 transformations. Okay? Now this could be something you're asked to do on a test to compare which one's better. This is X. This is ln of Y. This is natural log of X. This is natural log of Y. If you look at the derivations that we did, trying to make sure that's clearly marked here, that this is that's Y. One was for exponential, the other was for power. Okay, now if you look back at those notes that we took, you'd see that would be, if that's linear, then we're going the exponential route. If this one is more linear, we're going to go the power route, and it certainly looks like the power model that compares the natural log of both variables is a little better. Now again, I'm not going to use it to make a prediction here because I've got another pattern to my residuals that I don't like, but it's there. I just bring that up because I don't want you to think, oh, R squared's 100%. Lovely, it's a perfect association. Well, our residuals have a pattern. It's not ideal. They're very small. I'm not super concerned about them, but they're there. Okay? Here are the numbers that we need, but with the power model, this is what it would look like. I could predict the natural log of its period of revolution, how long it takes to do a revolution. I've got a y-intercept of 0.0002544. plus a slope of 1.4986. And this is where you have to be, again, so careful. We were looking at the power model, which has the natural log of both variables. Natural log of x goes there as well. Okay? We've got to watch out for that. This compares ln of x to ln of y. So the very first thing, if I had a distance from the sun for a planet, I need to plug it in for x. Very first thing is to take the natural log of that number.